Thank you very much for your nice introduction. I'm Annatoma from University of Texas, El Paso. Today I'm going to talk about flexible inkjet printed gold-based electrochemical sensor for aqueous lead detection. I'm going to present my talk based on this outline. Lead is a global major public health concern. So it is an irony that 1 in every 3 children in today's world has excessive blood level that is greater than or equal to 5 microgram per liter. So which is a major concern. According to World Health Organization as well as CDC, they state that both regional and global interventions are required to face this issue. In addition to that, unfortunately, last year, the 3 most popular lead sensing devices were recalled by FDA due to inconsistent and unreliable behavior. So here we need to work on developing a low-cost, sensitive, reliable, and consistent lead sensing device as soon as possible. So here is our approach, that is inkjet printed electrochemical sensor. And why are we choosing this technology? Because right now, most commercially available sensors are either screen printed electrodes or lithographic process. So we are focusing on inkjet printing because it offers high resolution, low cost, low material waste, wide variety of materials, as well as it doesn't require any hazardous material or green room facilities. So we are really focusing on that. The one major challenge here is in terms of microfabrication. So we're still working on that. I'm going to talk about it later. So our previous work was inkjet printed electrochemical sensor on shape memory polymer, which we reported at IEEE Sensor 2021. And there we focused on inkjet printing silver based. Actually, this is not gold again, but I will discuss why we use silver because it is low cost, right? But our gold electroplated sensors actually behave like bare gold sensor. Those are available commercially in the market. So we offer this combination because of simple and quick fabrication as well as miniaturization of the device, because we got like 58% reduction in terms of dimension for our electrochemical sensor. And also we were able to see increased effective electrode surface area compared to lateral surface area because of that crunching and twisting mechanism of shape memory polymer. And we were able to see a very good performance for our fabricated electrochemical sensor in case of 14.4 microgram per liter lead. And we have chosen this dimension because in the United States, according to US Environmental Protection Agency, the maximum allowable lead level is 15 microgram per liter, but we are currently working to push this concentration as low as possible. So here we are for our inkjet printed electrochemical sensor on shape memory polymer. We observe that the shape memory polymer is making the sensor really rigid, which might be a complex situation in terms of scalable printing, though we observe very optimum results. So we tried to play with it and explore it a little bit. So we started working on flexible substrates. Now, the technology is same, that is inkjet printing, and for substrate we have chosen Teslin, which is PPG SP600. And the reason for choosing the substrate is it has a porous and uncoated nature, which allows it to absorb maximum silver in nanoparticle inks inside it, so that it can bond very strongly with the substrate, which increase the adhesion of the print sensor. Because what happens to flexible sensor is it has really less adhesion, and when we are doing some electrochemical analysis, we just actually break or damage the electrode in the processes. So the dimension of our final device is 12 by 8 by 0.52 millimeter cube, and our effective electrode surface area for this sensor is 3.41 millimeters square. Though it has some challenges, as I have previously mentioned, it requires very gentle and delicate post-processing steps. So we need to be very careful with the flexible sensor. Now for inkjet printing on Teslin SP600, we need to first optimize the parameters of inkjet printers because no one has reported, inkjet printing on Teslin SP600. So we went through the critical observation. I have chosen platen temperature as 40 degrees C and Kurdish temperature as 35 degrees C, while we require drop spacing 10 micron, and we need to print 2 layers. As I have previously mentioned, Teslin is pretty much porous material. So then we get the resistance as 0.2 ohm per square. I'll discuss a little bit about it. When we were using shape memory polymer, the drop diameter was approximately 75 micrometer. So it was pretty big, but when we convert it to Teslin SP600, the drop diameter is only 45 micrometer. And we try to figure out the conductivity in terms of different drop spacing, such as for 25 micron, when we observe like only 45% overlap, we took the same images and we can clearly see some breakage in there. There is no conductivity at all. It is infinity. In case of 20 micrometer, when the overlap was 56%, we can still see some breakage, and there were no conductivity even after printing 2 layers. In case of 15 micron spacing, when the overlapping was 67%, still there were breakage in the same images. And finally, when we choose like 10 micrometer, which is almost 78% overlapping of 2 adjacent drops, we can finally see a clean same images, and the resistance is 0.2 ohm per square for 2 layers of printing. So here I will describe the fabrication processes in details, because it's pretty crucial when we are dealing with substrate like Teslin, and we are also planning to work on electrochemical analysis. So first we make the CAD design using any software available. Pretty much I use GIMP. Here, after that, we take the bitmap images and we use diametric materials printer to make this silver printed pattern. Again, I'm using silver to make the device low cost, which pretty much behaves like bare gold, because we do the electroplating of gold, which makes it way less expensive compared to the existing one. So we pretty much put the printed pattern on the hot plate, where we cure it at 120 degrees C for 20 minutes. After that, our electrodes are conductive, and we get the resistance as like 0.2 ohm per square, and this is like 2 layers of printing. And we cover the working and counter electrode with a masking tape, and only reference electrode is exposed, and we expose it deliberately to do the chlorination processes, because we want the reference electrode as silver chloride reference electrode. But here also we need to be very careful. It is we can only immerse the reference electrode for 30 seconds, because if we exceed the time, it will break the electrode and we might compromise the conductivity. And after that, here I want to note one more thing. The reason for choosing Teslin was it was porous, and it really creates a strong bond between the inks and the substrate, which is evident here because we put a masking tape on the working and counter electrode, and we pulled off the masking tape, but adhesion was strong enough that it didn't do any damage to working and counter electrode. After that, we use the gold electroplating technology. Again, to make it cheaper, we use silver ink, but now we are gold plating it. And finally, here is our gold working and counter electrode and silver chloride reference electrode. So we have done the fabrication processes, but we need some validation, because again, we have used some potential timing and potential applied voltage for chlorination and electroplating. So for validating the fabrication processes, we went through the energy dispersive X-ray spectroscopy. And we also tried to compare it with our rigid ones, because we have seen very optimum results for our rigid sensor. So this is for the cured silver electrodes, where we can see that 41.7% silver is there for the cured silver electrodes, and this is for the rigid one. It is pretty much same. And then it should be same, because we have done the curing and all that. So for chlorine, we can see that 11.8% chlorine is there for silver chloride reference electrode. For rigid one, we can see it was 7.9%. Well, we can see some increase, but I think for both cases, it was in an optimum amount to do or go for further electrochemical analysis. And for gold, it was 6.8% for flexible, as well as for rigid, it's not same there, but it's 9.9%. So pretty much at optimum level for going further CV analysis. Now, the flexible electrochemical analysis was characterized using CV, cyclic voltammogram analysis. And here also, I try to compare it with the rigid performance, the performance of a rigid fabricated sensor. So I have actually characterized the sensor in 3 different ways. The first one is, of course, blank, where I have only used optimized drinking water, which is like 0.1 molar hydrochloric acid without lead. Then I have used a very high amount of lead, such as like 3 millimole, which is 3,600 microgram per liter, to see how it is behaving. And after that, I went to like 14.4 microgram again, because according to US EPA, the level was 15 microgram per liter, but we were working hard to push it like further. So this is for rigid, we do not see any peak. This is for our flexible, though it is kind of like noisy, but I will say like I haven't seen any peak. I'll talk about this CV in the next slide in more detail. So this is for rigid, for 0.1 molar hydrochloric acid with 3 millimole lead, where we can see some deposition and a stripping peak. But I will say from my analysis that due to some contaminated, the peak is shifted a little bit to the left. This is for the flexible one for the same concentration. We can see some peak, but then again, in this region, we can see some flattened area where some information is missing. I'll talk about it in the next slide. So this one is for CV for 14.4 microgram per liter, where we can see a very nice deposition and a stripping peak. This is for our flexible, this was for our flexible one for 14.4 microgram per liter lead. We can see the peak is flattened, but then again, we can see at approximately 180 millivolt some peak. But like we have validated our fabrication processes, right? But something probably went wrong, because we do not see as optimum result as we were expecting for our flexible sensor. So what went wrong? We went through some further observation, and we see that, well, the substrate was porous, so it was actually absorbing the water while we were performing electrochemical analysis. So we wanted to take some pretty quick samples of 5 centimeter and 5 centimeter. We put that in 0.5 milliliter DI water, and just after a minute, we saw that the conductivity is way higher. It is like 4.48 ohm per square resistance. So it is, everything is shorted right after a minute. So how to solve this issue? Because the existing technology that offers like coating the substrate, we didn't want to do that, because that's how we compromise the addition of the printed pattern on the substrate. So our Captain definitely works, but we need to figure out a way on how to maintain the adhesion plus get rid of the water absorption problem. So here is our technique where we are printing the patterns on the Teslin based on our optimized parameters and all that. And then we put like Captain tape, which is laser cut based on our design, put it on that so that the electrodes are exposed, but the rest of the area is covered with the Captain tape. So we are not compromising the adhesion, but we are also not getting rid of water absorption problem. So the preliminary data shows very promising output, and we are pushing the concentration again to 5 microgram per liter. And so we have presented here the optimized inkjet printing parameters for inkjet printing on Teslin PPG SP600. We have also measured the drop diameter, drop spacing, and printed layers. And we have also figured out the water absorption problem and the solution of that problem. So that's pretty much about my presentation. Thank you for your attention. I'm opening the floor for questions.